Good morning, everyone. I hope you've all been enjoying today's event. The next lecture is from Günter Ziegler, a professor of mathematics and the current president of the Free University of Berlin. His interests are mainly in connection of discrete and computational geometry and topology, and he has received numerous prizes, among them the 2001 Leibniz Prize for his research. Along with Martin Anye, he wrote the famous book Proofs from the Book, which has been published in 14 different languages by now and is in its 6th edition. His lecture today will be on Proof, Mistakes, Publications, and Pizza, Mathematical Research in Practice. And at the end of the presentation, there will be a discussion led by Professor Bernardo Costa, whom some of you may already know from a previous interview today, and Claudio Verdon, an alumni from our university and PhD student at Technical University of Munich. For this lecture, we have a small request. Please turn on your cameras if you can. And Professor Günter Ziegler, you can start now.
Now I hope that you can hear me.
Yes, we hear you. Okay,
wonderful. Thank you very much for the invitation and for setting all of this up. This is a marvelous opportunity. I'm here in Berlin, Germany, and I have the opportunity to speak to all of you about, well, I was supposed to talk about mathematics, and I thought I should take a rather general topic and I can tell you some stories and some insights about how mathematics is done, and I thought I should try and tell you a little bit about the real story and not only the myth and the sort of the general idea for the media. Let's see. This is the plan for my little lecture. I will start with the myth, what everybody is supposed to believe about mathematics. And then I'll talk about the reality in contrast. And I will show you things rather concretely with one conjecture about pizza and sandwiches. And then we will look at how mathematical research gets written and refereed and published, which is all this process which is supposed to guarantee that in the end everything's correct and valid for eternity. And then things go wrong, and I will talk about why things go wrong, and again give some examples for that. That's the plan. Now, if we start with the myth, then I mean, the mathematician is portrayed as sort of in various ways. One portrait was that he's a mythological beast, half a chair, half human, and that everything he produces, and the stereotype is he, so he's also male, and everything in the end is perfect, even if the desk more or less looks like what you see on this picture, which is perhaps not quite as perfect as it should be. There's other descriptions. Paul Erdős, a legendary Hungarian mathematician, has claimed that the mathematician is a machine for converting coffee into theorems, which also tells you that the relevant thing in the end is these theorems, which are sort of the output of whatever we use at input, and that's the product that we are trying to produce. This here is from a real interview which happened a few years ago, where an Israeli mathematician was on the radio in Israel, and he told the journalist from the radio that Euclid proved more than 2,000 years ago that there's infinitely many prime numbers. And so the journalist asked, well, and so is it still true? And we tend to laugh about that because we know that, of course, if something has been proven, then it's true forever. At least that's the idea. And part of my lecture will be to argue that it's just not quite as simple. And some things that have been proven or claim to be proven even 2,000 years ago are not valid anymore. And these things can happen. mathematics is a subject that's much more alive and much less perfect than we usually try to say. So what's the criterion in the end? We always claim that things have to be correct, and that's the most important thing. But this is a quote from a famous lecture and book by G.H. Hardy, a British number theorist, who says that the mathematician's patterns have to be beautiful and they must fit together in a harmonious way, and beauty is the first test. There's no permanent place in the world for ugly mathematics. I believe this is true, but if beauty is the first test, does this still say that the second test has to be correctness, or perhaps is correctness the first test? I don't know. Sometimes these things just don't fit together. And there's various experiences that tell us that we have to be a bit more careful. This is drawings actually from proofs from the book. The person on the left is Paul Erdős, the Hungarian mathematician. And Paul Erdős told this story of the book, which God has, which contains the perfect proofs in mathematics. And again, the idea there is that every theorem has a perfect proof, and God knows these proofs. Actually, Erdős always said that as a mathematician, you don't have to believe in God, but you have to believe in the book. And the book is this book of perfect proofs in mathematics. And again, if you do it that way, beauty is the most important part, and perhaps correctness, whatever that means, then is the second one, but it's not quite mentioned in the same way. Other people agree, and so here's my last quote for the introduction. Paul Dirac actually is a physicist, a rather famous physicist, and he said that there's theorems that are too beautiful to be false. And whenever he was doing physics, it's more important to have beauty in your equations than that they really fit the experiment. And if everything goes wrong, you redo the experiment. I don't know whether physicists would still agree with that, but that says that even the physicists agree that the beauty of the equations is what counts most. We can discuss about that later. However, if you take this as sort of the general picture and the myth, then the reality is that mathematics actually starts with mistakes. So if you take the beginning of mathematics as a science is Euclid's book from, I don't know, 250 before Christ, which starts with the construction of the triangle with 3 equal sides. And so this is proposition 1 in book 1 of Euclid's Elements. And whatever he does there has been criticized a lot, because in the end, the way Euclid does it, it's not correct because it's not complete. And his axioms are not good enough to really guarantee that the 2 circles intersect that are constructed there. So it's just a small hint, but even at the beginning of mathematics with Euclid, it starts with gaps and with mistakes and with things that are not quite correct and complete. And in that case, it needed much more than 2,000 years until, I guess, Hilbert around 1900 set up the axioms for plane geometry in a way that things were really correct and complete. So it took a very long time. Here's another example, also from antiquity, where Aristotle claimed, the philosopher, he claimed that out of the regular solids, which were known at the time, only the cube and the tetrahedron really fill space. So he was talking about the regular cube and the regular tetrahedron, and we all know that the regular cube fills space, so you can take little cubes and arrange them in a way that it completely fills space. but actually if you do the computations, you realize that you cannot fill space completely with regular tetrahedra, basically because the angles don't work out. But for that, you have to work out the angles, and for that you need trigonometry, which Aristotle didn't have. And so it was discovered only in the 15th century that this claim by Aristotle plainly is not true. And that's one of the unsolved problems around. We still do not know how well you can fill space if you have regular tetrahedra. There is a doctoral thesis by Elizabeth Chen from 2008, where she constructed a packing of regular tetrahedra, actually always pairs of tetrahedra, which fills space up to 78%. But the gap between 78% and 100, we don't know. So in some sense, Aristotle made a claim which was wrong and posed a problem which we still cannot solve. And we are not even really close with methods to really answer this problem. And actually, this is also part of Hilbert's 18th problem. So this is really famous problems in geometry, which start out with a mistake by Aristotle. Here's another one, also a classical mistake. Archimedean solids have been studied since, well, probably Archimedes. So again, classical Greek mathematics. And it took from Archimedes' time until Kepler proved in 1619 that there's exactly 13 types of these solids. So an Archimedean solid is basically the type of solid that you see in this picture, which is from Kepler's book, and which shows these 13 types. And Archimedean solids, they have faces which are regular polygons, and around each vertex, they have the same sequence of regular polygons. And so it was hard work and proved by Kepler that there's exactly these 13 solids if you ignore the Platonic solids, and if you ignore the prisms and well, I think it's the prisms and the anti-prisms, which are also not counted. And then you have these 13 examples. So this is Kepler's theorem. Kepler is the same guy, the astronomer, who found out that planetary motion is on ellipses. So Kepler was an amazing astronomer. He was also an accomplished mathematician, but not everything he was doing was very convincing in particular in the connections between astronomy and Platonic solids. Why am I telling you that story? Well, basically because this classification of the Archimedean solids is very famous work by Kepler, which has been reproduced in all detail. If you want to read in all detail, you can look at the book by Cromwell from 1999. So this is the 2 pages from Cromwell's book, and there the proof is given in all details. Nevertheless, the result is not correct. There is a paper by 10 years later by Branko Grünbaum, famous geometer from Seattle, Washington, who described this as an enduring error because over far more than 2,000 years, this classification of the Archimedean solids has been round and it's not correct. And the reason it's not correct is that there's a 14th solid which everybody overlooked or ignored, or a combination of the both. And this is a description of this 14th solid. So what you see on the left is one of the classical examples. Actually, if we go back here to Kepler's, it's the number 1 in the upper left corner of Kepler's classification. Actually, no, that's wrong. It's the number 10. It's in the center on the right-hand side. That's this polyhedron number 10. And what you can do with this polyhedron number 10 is that you can take the upper half and rotate by an eighth and reassemble. And then you get a new polyhedron. And that's the one that's shown here as number B, which is really different if you think about it for a while. And it was missed in all these classifications. So again, this is from my area in discrete geometry. We have these mistakes which have been around for centuries. Then at some point, someone finds the counterexample. In this case, this is by Somerville, 1906, who probably was the first person who described the counterexample. But then still nearly 100 years later, this incomplete classification is republished again. So it's really a sad story, and it should make us think about how we are doing with mathematics, which should be perfect and correct for eternity. This is the classical stuff. Let me now go to very recent stuff. And this comes from an area that I've worked a lot in, which we call topological combinatorics, which was founded by a famous paper by Laszlo Lovász in 1978, where he solved a graph coloring problem known as the Kneser conjecture, which had been very famous. And Lovász's solution is famous because he solved it by using algebraic topology, which really no one expected at the time. And Lovász's solution is beautiful, and it is correct, I should say. And it was the beginning of a whole area of mathematics, which became a research area where you use topological tools to do things in combinatorics and geometry. It became an industry because people started to understand how to use these tools and how to set things up to prove things using the Bohr-Segulam theorem. And actually, it also became textbook knowledge because there was then a textbook by Jirka Matušek. And it also became child's play at some point when people really understand things. So here's the textbook by Jirka Matušek called Using the Bohr-Segulam Theorem. If you're interested in those things, look at the book. It's one of the most beautiful math books I know. And this is the proof that this is child's play, because I found this book on eBay. German eBay sold in there, if you can see the category under books, and the subcategory is children's and youth literature, subcategory fun and games, and subcategory knowledge for children. So this book is knowledge for children. That's what we learn from that. It's also knowledge for grown-ups. Now here's a problem, which basically is one of these topological combinatorics problems. And I start with a pizza, where the question is, if you have a pizza, can you cut it with one cut into two equal halves? Now, of course, you have to think about what you mean by equal. First, this is sort of the mathematics version of a pizza. It's just a polygon. And by equal halves, we mean, can you cut it into two halves that have the same area? And the answer is yes, and it's reasonably easy. You just do a horizontal cut. Well, this one isn't really good enough, but if you slide this cut from bottom to top, then you at some point find a cut which cuts it into two halves of equal area, right? And indeed, this is easy. And if you think about it, you realize that what you've just used is the intermediate value theorem, which goes from lower side is smaller to upper side is smaller if you slide the horizontal slide. So this was easy. Again, now we make it more difficult. You have one pizza again. You're supposed to do two cuts, and you are supposed to cut the pizza into 4 parts of equal area. How do we do that? Well, again, it's not hard. You first cut into two parts of equal area, and then you do a cut which takes the upper half into equal area, and then perhaps you try and rotate this cut. And if you think about it a bit, you realize you can rotate this from one part being larger to another part being larger. And so by rotating this cut, in the end, you find a solution into 4 pieces of equal area. And what you have used is the intermediate value theorem. So actually you have used topology, because that's a intermediate value theorem uses continuity. So it's a topological theorem. And so this was using topology to solve problems in geometry or in combinatorics. Now, the next step would be again a pizza, 3 cuts. Can you cut into 8 equal parts? And the answer will be no, because if you cut a pizza with 3 cuts, all you can get is 7 cuts. You never get 8 pieces. And if you think about it a while, you also you cannot always get 7 equal parts, and that's not possible either. So there's all these problems around about cutting stuff, and sometimes this can be done and sometimes it can't. Here's the most famous one. It's the so-called ham sandwich theorem, where you have a sandwich which consists of 3 different things. I don't know, the bun and the upper part of the bread and the lower part of the bread. And now the sandwich is 3-dimensional, I should mention, because you can see that from the picture. So it's a 3-dimensional sandwich. And the question is, can you take any sandwich with 3 parts and take 1 cut and cut each of the 3 parts into 2 equal size parts? And that's a famous theorem due to Steinhaus and Banach, 1938, known as the ham sandwich theorem. And the important part here is that you really need a topology theorem to do this. And basically, you use the Borsuk-Ulam theorem, or a version of the Borsuk-Ulam theorem, to do this. And there's a d-dimensional version which says if you have a d-dimensional sandwich which consists of d different parts, you can make 1 cut, and that cuts each of the parts into 2 equal halves. So that's the d-dimensional ham sandwich theorem. We've just done the 2-dimensional one. This is the 3-dimensional, there's the d-dimensional one. And now we generalize. And here's the question. You have a sandwich or whatever consisting of j parts, and you're supposed to do k cuts, and you're in dimension d. Can you cut any j objects simultaneously into 2 to the k equal pieces by k well-chosen cuts in dimension d? That's the problem. Now, I don't expect you to work all of this out now, because it's not the subject of my lecture. It's interesting, one thing that was figured out by Edgar Ramos in his dissertation in Chicago in 1996 is that if the answer is supposed to be yes, then d times k has to be at least j times 2 to the k minus 1. That's a necessary condition. That's relatively easy. And now the question is whether that's also sufficient. So his conjecture was that if this little inequality is satisfied, then the answer is yes. And we know that otherwise it's no. And so this is Ramos's conjecture. And 1996, so this is 24 years ago. And there has been a number of papers about this, solving parts of this conjecture. So there was a paper by Ramos, 1996, with some special cases. There was a paper in Advances in Mathematics by Mani and co-authors, 2006. There was a paper by Radosevljević and Transactions of the AMS. This is all very good mathematics journals. There's another paper by Radosevljević rather recently, 2015. All of these papers prove special cases of Ramos's conjecture. They say that in case something is a power of a prime or special values, the answer is yes. Why am I telling you that story? Well, I tell you that story because we wrote a paper where we reworked all of these papers, and that's the major papers about this problem. And well, our wording was there that we give a critical review of the work on this Ramos conjecture, which concludes the documentation of essential gaps in the proofs for some previous claims. I hope you see that we were trying to be nice. If you print things, you want to be nice to people. And this is from this paper. It says we have to observe that quite a number of published proofs do not hold up upon critical inspection, and indeed some of the approaches employed cannot work. As some of these errors have not been pointed out in print, although they may be known to experts, we will provide detailed reviews. In other words, these 4 papers are wrong. And they are so badly wrong that also the method of proof in these papers plainly doesn't work. And so you can ask how that could happen. Definitely this does not fit together with the myth, which says that in mathematics we prove things and then they are true for eternity. So what happens? There was papers published in respected journals. How can this go wrong? Now, I want to illustrate this a bit, but perhaps it's not so nice to illustrate that with other people's work. So I want to illustrate, and since there's also undergraduate students here and listening, I have to show you how this process works of how do you get a paper into print. And here's an example. This is a paper that I wrote with 2 co-authors. Pavle Blagojevich is a friend and colleague in Berlin. We worked a lot together in topological combinatorics. Wolfgang Lück is a famous topologist in Bonn. And for a later part in the story, perhaps it's important to say that not only I, but also Wolfgang Lück has a Leibniz Prize, which is a big prize in Germany for all of the sciences. So, so this is one of our papers, and was a paper on highly regular embeddings. I'm not explaining now what this is. If you can see the screen here, you see that there's complicated topology going on. For example, Borsuk is mentioned in there again. Now, we wrote this paper, and what you do is if you finish a paper, this is a preprint, so that's not checked yet by the experts. You put that on the archive, which is a preprint server where the whole world can see it and read it and check it and send you comments if they have any. So this was a preprint from 31st of May 2013, a 20-page paper in algebraic topology, which we deposited there. Now, there was no major comments coming in. We did some revisions, which you can also see there a year later in 2014. We took our paper and sent it to a journal. And the first journal we sent it to was Mathematische Annalen, who sent it to referees. And the referees said the paper is nice, but it's not quite good enough for Annalen, so they didn't want to print it. Happens. So we sent it to a different journal, namely to Transactions of the American Mathematical Society. And the referees for Transactions liked it and checked it and recommended that the paper should be published after some minor revisions that the referee wanted to have done. And so we did that. And after that, the paper was published in Transactions of the American Mathematical Society in May 2015. So it took 2 years from first version of the preprint to publication in a very good journal. In mathematics, this is usual, because in mathematics, things are checked and verified on the way to publication. That's different from, for example, what people do in biomed sciences, where they always want things published within 6 weeks. And of course, you can't redo lab experiments within 6 weeks. That's a big problem in the moment, in the current crisis, but not our topic for today. So that's the story of this paper, published in American Transactions of the AMS. After that, the paper is reviewed, for example, in Zentralblatt, which is one of the 2 sources where every mathematical paper is reviewed. And this gives a short description of the paper in that Zentralblatt database. The other database around is Mathematical Reviews, which you can access online by as MathSciNet. And they also, the referee for MathSciNet also reviewed the paper and reported about the main results. So that's the usual lifetime of a paper: preprint, submission, referee reports, publication, review in Zentralblatt, review in Math Reviews. And at that point, usually the story is over. In our case, it wasn't, because this is May 2016, so 1 year later, we got a little email by a guy called Michael Crabb, a retired topology professor from Edinburgh, who I had never met and still haven't met, who says that he looked at our paper and found out that our computations didn't fit together from what he had computed. And he says he tried to figure out what was wrong and sort of did it on a very simple, small example, and still couldn't figure it out. And he attached a 2-page PDF and said, perhaps you can find an error in what he had written. Now, if you get an email like that, you don't like that, because it sounds like there was something wrong in our paper, right? Well, it turns out that, of course, we immediately checked what was wrong there. And the bad news is that there was nothing wrong in Michael Crabb's computations. He was right. The good news is there was also, we didn't do a mistake in our paper either, except we used someone else's work. And the paper that we had used was a very well-known paper in topology, a paper by a guy called Hung from Vietnam from 1990. And this paper by Hung had been quoted and used again and again by many people, famous people, Vasiliev and people like that. And apparently no one realized that Hung's paper was wrong. And the reason why no one realized that was because everybody was using his main result, and his main result is correct. Whereas we had used his intermediate results, and his intermediate results, there's bad mistakes in there, which also means Hung's paper is not correct. And so one tries to understand what is wrong with Hung's paper. And this here is a footnote at the end of Hung's paper, which says that this is really a paper that was from the author's thesis in 1982 and was submitted to a journal and then apparently forgotten. And then perhaps when they discovered that, it was rushed to print. Anyway, what has happened since Hung's paper was wrong, Also, our paper was wrong where we used Hung's result, and now that has to be corrected. And that means we're in the next version of the life cycle. And in the moment there is a paper, and this is growing into a book because it's a very long paper where the previous authors, together with Michael Crabb, who had told us about the mistake, and with Fred Cohen, who is a senior person in the area, we are trying to rework the whole thing. We are reproving Hung's result now in a completely different way. And so you see, life goes on. Mathematics has to be revised. It's not true that things, once they're published, they are correct, but then mistakes may turn up, and then things have to be reproved or corrected or retracted or whatever is correct. In this case, this is current work by these 5 authors trying to revise our previous paper, but also redoing Hung's previous paper. The preprint is in the web on the archive if you really want to look at that, but we are still extending that by a new introduction. And so I think this will be a book rather soon on these previous mistakes. Anyway, I'm getting to the end of my lecture. I just want to show you that also in literature, this problem has shown up. Now this is in German, but it's from a story by a German author called Helga Königsdorf, who was rather famous as an author, but she's also a mathematician. And so this is a story that was called Lemma 1, where she describes how mistakes in mathematics could come along. And her description says the theorems and lemmas in a mathematical work are numbered. They are closely connected. So you find in the proof of theorem 11, the wording which says that as you see easily using theorem 9. In the proof of theorem 9, it says this follows from lemma 3. And in the proof of lemma 3, it says this is correct because otherwise we would have a contradiction to lemma 1. So there can be a very convoluted sequence of arguments which says that in the end, everything in the paper is only true if lemma 1 is really valid. So if there's no proof, no mistake in the proof of lemma 1. This is the beginning of her story, and the next sentence says lemma 1 was wrong. And so this happens in mathematics again and again, that lemma 1 is wrong. So here's an example reasonably recently, a paper that was in the archive by an author, which then the author had to withdraw because he realized that there was a signed error in equation 1. So there might be a mistake right at the beginning, which then invalidates everything else. Same thing happens in famous works in algebraic topology. In this case, this is a slide by a lecture by Wolwodsky, a Fields medalist, where he explains that in a famous paper by Spencer Bloch from Chicago, there was a mistake in the proof of lemma 1.1. The proof could not be fixed, and almost all the claims of the paper were left unproven. So this happens in mathematics. It's part of real life, and we have to deal with it. One way to deal with that is a completely new topic called formal proofs, where in the last 20 years, people have worked hard to set up proofs in such a way that they are formal, and formal means they are so formal that a computer program can read and verify them. And you could stare at this for a while. It's not very easy to read, but this is a formal proof for the fact that the square root of 2 is an irrational number. It's one of the very early proofs we all do in mathematics. Now this can be written down so formally that in the end a machine can check it. And that's one direction out of these mistakes in mathematics, that we say things are finally established only if in the end we've been able to do a formal proof, which is a proof that can in the end then be checked by a computer program. And these special computer programs, they are so constructed that they can even check themselves and check that they do the right work. This is a long story, and we could talk about formal proofs. I'm not an expert there, but I admire what people are doing, and they're doing very quick progress. I just want to summarize and saying that making mistakes is not necessarily a bad thing, but it's just a part of being creative. We try out ideas, and if you want to be creative, you have to make mistakes. Finding mistakes is part of science, and that means it's also part of doing mathematics. It's an important task. If you make mistakes, it's very important that you're willing to acknowledge mistakes, that you also announce if you've made mistakes, to help people who rework things, to see where mistakes are. From mistakes one can learn, and one must learn. That's again an important part of doing mathematics. One might even be inspired from mistakes. Perhaps many of you know the story of the proof of Fermat's last theorem by Andrew Wiles, where the first proof he gave was wrong and was badly wrong, and there was no way to repair it. But from analyzing this wrong proof, Andrew Wiles in the end got the idea for the correct proof, which was even much more beautiful. And so even out of mistakes, one can get inspired for new things. And that's the end of my presentation.
Professor Günter, I think everyone enjoyed you very much, your lecture. And we have two questions from Tiago Ritel from YouTube. How often are mathematical results thought to be correct actually proven wrong later? And are these mistakes fundamental, or under a different set of axioms are actually correct?
It's a difficult question. So the question, how many, one could ask how many percent of papers published in good journals are wrong. And I think there's no really good analysis, and it's very difficult to do that, but it would be interesting to do that. Would be interesting because, for example, in the biomedical sciences, there was a famous study by Ioannidis where they tried to recook papers in science and found out that something like 60 or 70% of the papers could not be reproduced, which is sort of the biomed criterion of being wrong or being useless. I think in mathematics, we don't have that problem. I think that probably most papers have some little things which are perhaps not quite correct as stated, but that doesn't really count. I think that most papers, research papers in mathematics are correct. But if we would really rework things in detail, we would find out that perhaps 1% or 2% or perhaps 5% of mathematics papers have serious problems or gaps, and one could learn and one could make progress from really analyzing these gaps or mistakes and going on from there. The problem, of course, you don't know which one they are, and so that gives a certain sense of insecurity. I mean, one observation I have made is that there's certain corners of mathematics where there's more mistakes than in others. And I showed you this area of topological combinatorics, which I think is very dangerous because there's people who use tools from topology on combinatorial problems, and some of the people in the area just were too careless and didn't worry enough about what's the prerequisites and what's the conditions that theorems can be applied. And I think there's more mistakes in topological combinatorics than in other areas of mathematics. In the end, I think there's the part from, there's a second stretch that I've not talked about, which is sort of from taking research mathematics, and at some point this will get textbook knowledge. And we would hope that by the time things get into textbook and are explained in a textbook way, they are really reliable and they've been looked at in enough detail and by enough people that this is then, in that sense, really established knowledge that we can rely on.
Another question is, what about difficult subjects like inter-universal Teichmüller theory that just a few people can barely understand what's going on? If it's published, would it be reliable? Would it be a lot of mistrust on the paper?
Good question. I mean, this inter-universal Teichmüller theory, this refers to work by a mathematician from Japan who claimed that he can prove the so-called ABC conjecture. And there's been a huge discussion about that over the last few years. This work is definitely very complicated and it is definitely not well explained and it is hard to access. And my understanding is that by now people have identified substantial mistakes in this work, which really shows that the work is not correct. And at the same time, this work is now being published in a journal nevertheless. And if you take these pieces of information together, then I think that tells you that even though this is eventually published in some journal, this does not guarantee we should believe that it is correct, but we should rather look at the detailed arguments and analysis that has been done, which points to substantial problems in there. But in general, I mean, of course, it's always the more people have looked at something and the more people have verified it or say they've understood it, the more reliable things should be.
Okay, and the last question, so we can start on the discussion, is from Victor Luis. On the other hand, what about mistakes that arise from questioning axioms and simple concepts that are assumed at some point in time, but are later questioned? I think the argument Euclid's work was a book of instructions for geometrical construction, for example.
I mean, part of the truth is that in mathematics, basically never we really work starting from axioms. And my impression is that for sort of working mathematicians, we have a full agreement about the axiom that we use and the set theory that we use and the logic that we use. And on the one hand, we all believe that the axiom systems that we use are consistent, but since Gödel, we know that this cannot be proved. So there's a certain danger in there, but everybody thinks that we are on a safe side there. But that also means that we are always sort of working very high up in the tree of mathematics. And there's always the question, how much have we really understood and how much have we verified of all the things that we use? And the examples I gave you in this work on highly regular embeddings, the mistake was in stuff that we have used that was not sufficiently verified. However, I've never seen an example where this really started out with that there was a problem in the axioms used, but the problems are always much higher up in the tree in my experience.
Okay. Thanks again. And Professor Bernardo and Claudio, you can follow with the discussion.
Okay, so do you hear me?
Yes.
Yes. Okay, so yeah, first of all, Professor Günter, thanks a lot for your amazing talk. And yeah, I don't know, I was thinking and talking a bit with Bernardo, and I think I have several questions to you, but so the first one, I would say I would like to do some, to discuss maybe, let's say, the similarity with music. It's something that usually people do for mathematics. And then one thing I would like to ask you is like, how exactly the appreciation of a mathematical proof, I mean, how much math experience or maturity does this require? Because, for example, if you think about music, if I think quickly now, I would say most of the people would agree that, for example, the Nocturnal by Chopin, it's something more beautiful than the Art of Fugue by Bach. That's something that takes years until you feel comfortable to enjoy. So how is it for, like, in mathematics for you?
I think a lot of things in mathematics are in the end a question of taste. And this is not only for looking at proofs, but also for theorems. The question, what's an interesting theorem? What is a beautiful theorem? In the end, it's a question of taste. I think it depends on experience, and it depends on what you have seen and what you've compared, what you can compare to. So to a large extent, I think there is things that are question of taste, and I think that's good and that's important, because in the end we want to do not only correct mathematics, but also mathematics that matters, that's interesting, that's perhaps beautiful. And interesting and beautiful are not fixed criteria, and different people have different tastes, and that's also why mathematics develops in different directions. Of course, on the mathematics side, we still have the things that things have to be correct, and music doesn't have this type of fixed framework, and so there's really differences there.
Yeah, that's true.
So maybe I can chain now with some question. I was thinking about the proofs from the book, and I would ask you if you ever thought about writing the problems from the book. Do you think there are beautiful problems?
I think so, but that's even much more a question of taste. It's hard to assess because, I mean, with the problem that we have with problems is that, of course, we don't, problems are in particular interesting if they are not solved. And if they're not solved, then we also don't know how difficult they are, and we don't know what will be really needed to evaluate them or in the end to solve them and all that. So there are also much more questions of taste in the end. I got into a real quarrel at some point because I have claimed that the 4-color problem was a bad problem. Because you can see that in the end, I was arguing that because you can really see that in the end it doesn't have a good solution. There's no really elegant proof for that. But I know that there's people who would wildly disagree and say the 4-color problem has inspired all of graph theory and inspired lots of people, so it's a good problem. And perhaps it's a good problem exactly because it was never finished, in the sense that here's sort of the 2-line proof for it. What I've thought about was, rather than writing a book of problems, was to write a book of examples, or where we would take the most beautiful examples that we have in mathematics and illustrate them and explain them and say what can be shown about them. But in the moment, I don't have time to write books.
And how about counterexamples?
Well, examples are always counterexamples, right? Actually, there's, in the end, I mean, I think these questions of taste are important also in mathematics. There is books around called something like Examples and Counterexamples in Topology and Examples and Counterexamples in Analysis. And then the question is, what do you do with them, and do you like them? And that's in the end questions of how you do mathematics. So for the way I do mathematics, I think it's important to know the examples. And I test conjectures on examples, and I try and understand problems by working out small examples. And if you do, for example, if you do polytope theory, as I've done a lot, then you have to know the main examples in order to understand a lot of things. Whereas if you look at these like examples and counterexamples in topology or analysis, my impression was that there's lots of sort of very weird examples which are just constructed in order to disprove something or so, but which are not of independent interest. And perhaps that's also useful and that's also necessary. But then the question is, why do you collect the examples? And if I collect the examples for a book of the most beautiful examples, then that's just a different thing than collecting examples for topologists so that they know where the pitfalls are and where you try and give as many examples as possible.
Okay, I see. I mean, yeah, a follow-up question, maybe it's like, you mentioned the solution of the Kneser conjecture by using the Boschuk-Ulam theorem. And then there is this, I mean, there is this apocryphal story, so to say, by the Austrian physicist Wolfgang Pauli, who said like, yeah, I don't know, by checking some physics paper, he used to say, es ist nicht einmal falsch, this is not even wrong. And so was there a situation in mathematics that where you saw some technique being used in a paper and they'll say, come on, this is not even wrong? Was there a situation, a similar one in mathematics for you?
Oh yes, of course. And I think it takes some time to reach that stage where you look at papers and where you get quicker and quicker in evaluating things. And I mean, of course, that's a question of experience in the end, And if you've worked for many years in an area, then you know what the pitfalls are, you know what the methods are, and in particular, if this is on problems that you've thought about for quite a while, and then comes a paper which says here is a solution, then it saves you a lot of time if you have sort of this quick thing and says, well, this just can't work. And this just can't work is something you can sometimes say very quickly without even having read the details of the paper. And that happens, and I think in the end that's necessary and saves you a lot of time. Yeah, I mean, there's so many papers coming, and there's purported solutions to problems coming, and to sort out what's true and what's false and what's, you know, what can't even be true is an important part of the work.
So since you're talking about getting experience in mathematics, I wanted to ask you a particular question. How do you prove that you are capable of doing mathematical research? Because it's completely different for someone like a renowned researcher like Kepler having something false, and that probably didn't impact very much his career, and a young mathematician who has some proof that has been proved wrong. And more generally, what's the requisite, in your point of view, of proving to the community that you are a competent mathematician?
Well, I mean, the sort of the formal bar is to be a mathematician is to write papers and getting them published. What that really means is that you write papers and you send them to a journal where anonymous referees evaluate your work. And that means in the end, they answer where you are. And the interesting part of that is that, of course, the answer always is whether this is interesting and whether this is correct or at least plausible. And in the end, I think being a mathematician and doing mathematical research, you always have to deliver both. You have to deliver things that are interesting, and the measure for that is that there's other people who find this interesting. And of course, things have to be correct. And again, this is checked by others. However, on both parts, I think it's important also to be confident of one's own work. And if with your first paper and the first referee who says this isn't interesting, you just give up, then I think you make a mistake. Because in the end, you have to believe in yourself and in your own work, and that's more important than what other people say. So take other people's advice and criticism and judgment, take it seriously, but don't take it in place of your own. And for correctness of your own work, it's also important to know and to assert that the author is responsible for the work and for the correctness. And that's also an advice I got very early by journal editors who said, you know, you send a paper to a journal, the referees say, well, this is interesting and this is correct, but that doesn't prove it's correct. The responsibility is really my own as the author. And I should, and I mean, there's bad mathematicians who don't take this responsibility, and they think that the debugging and the criticism and all that would be responsibility of referees at the journal. It's not. but it's really my own responsibility to check my own work and to write it up as well as I can to convince myself and others that this is correct and complete. And only after I've done it, I should send it to a journal. But then, of course, having other people look at it as well, of course, is helpful and is valuable. And that's sort of then the next part.
Okay, I see. But yeah, what you're saying reminds me of a story I heard from like a student, a PhD student in the University of New York. He was doing a thesis trying to prove a very hard thing in symplectic geometry. And when he submitted, I mean, some important mathematician found a mistake, said this is too good to be true. And then there was a mistake. And so the guy had problems to graduate after 6-7 years in a PhD in New York. So, I mean, how do you see this situation? I mean, does this guy prove that he's able to do research in mathematics or not, or how this could be solved?
I mean, if this happens, and I'm sure this has happened, and this happens again and again, of course, it's very unfortunate. Most PhD theses or master theses I know, also they don't do one single thing, but they do several things. And you work on different problems, and you put a thesis together, or you explore an area and you get results there. And that also means that in the end, if there is a mistake in a thesis, that's unfortunate, and it's good to know that in the end, but it hopefully doesn't invalidate the whole thesis. And I think the process towards a thesis means learning and discovering lots of things, and even in the end, if there's a mistake in there somewhere, then hopefully it doesn't kill the whole thesis. Otherwise, this is of course very unfortunate. And I mean, in my PhD thesis, actually, there's one smaller chapter that's wrong, was discovered later. That's the chapter that's also not published as a journal paper. People do make mistakes, and that's part of the game. And it only becomes really critical if you're sort of this type of very ambitious, where in the end in your thesis you try and solve one result, and everything builds up to this one, I don't know, famous conjecture. And then of course you have to check very carefully that all the links in the chain are valid, because of course the whole thing can break if a single link in the chain breaks. But that's not the typical structure of a thesis.
Yeah, you're right. Okay, thank you for sharing your experience and your opinion. So now I think I would like to ask a question from the audience. Actually, we have a professor from the Federal University of Rio who is also here with us, Amiti Baya. He's asking, like, Hilbert did give his list of problems, and his state was impeccable and covered a lot of ground. Have there been any attempts since then?
There have been some lists. I mean, Hilbert's list is from 1900, and there's several people who made lists in the year 2000 on the occasion. And I mean, one list is this list of clay problems, these 7 problems which promised $1 million each, where only one of them is solved up to now. But there's also, for example, Stephen Smale published a list of problems which I think are and were very inspiring. And from Vladimir Arnold, there's a whole book of problems. So there's various things around if you're looking for, so to speak, famous problems. On the other hand, I think there's no single mathematician around who would have the scope that Hilbert had at the time, who really overlooked huge areas of mathematics. And I mean, he's famous for his work in algebra and in number theory and in differential equations and in mathematical physics and in whatnot. So this Hilbert list, I think, is something very special in mathematics history, and that just cannot be reproduced. And everyone who tried also realized that at the time.
Okay,
Great.
thank you.
Thank you, Günter. I have one last question for you. You spoke a little bit about the mathematical community and in several instances how this completes your role as the way you see beauty and the way the people value what you think. How does one get to know the mathematical community? And for you, what was the importance of the mathematical community when you were growing up?
Oh, I think it's amazingly important, and actually there's many mathematical communities, and on the way, since I've worked in different areas, I also realized that in some areas the community is much nicer than in other areas, and that's perhaps because there's just some senior guys or leading figures or so who set the tone. Altogether, I think mathematics is a community effort. And even if you look at things like refereeing processes for journals, I mean, the referees aren't paid, but that's part of community effort. And even if if you write a paper, I talked about the formal part. You submit to the archive and you submit to a journal and you get referee reports. The other thing is when you've finished a paper, you send it to people in the area and say, this is a paper I just finished. Perhaps you might be interested. I'd be very, very happy about comments. And that's actually also something that a bachelor student can do. If you don't know the community, look at the people who appear in the references of your paper, and that may be people who might be interested. And getting to know people, one way to do that is to send them an email and see whether you get feedback, which may be helpful or maybe not. And I think that's a good way of doing it. I mean, I myself, I was very fortunate to get invitations to conferences as a student already, or as a PhD student already. I was for the first time in Oberwolfach, and there I got to learn, got to know a lot of people in combinatorics that I've kept contact with for many years, and the same in discrete geometry. I mean, I met lots of the relevant people at conferences and talked to them and kept contact and exchanged papers. And I think even in these, perhaps even the COVID crisis we have now makes it even easier to just contact people over the internet or over, with all the communication tools we have, and to, since we can't travel that much in the moment, it's a good occasion to be less shy and to just make contact with people who might have interesting things to say about your work, and see how things develop. After all, this is all humans around, and many of them might be interesting to learn about what you've been doing and might contribute valuable comments. With this comment I had made, I mean, my first book was this book on oriented matroids, and at the time this was a rather hostile community where the people who had invented oriented matroids didn't like each other and were fighting for priority and all that. And then I moved into polytopes and into discrete geometry, and there everybody was so nice and so so sharing ideas, and it was just wonderful, and I enjoyed that. And I think part of finding your own area in mathematics could also be finding an area where you have interesting people to talk to and communicate with, and where you feel working the next years you'll have interesting and nice colleagues around. I think that's part of life also in mathematics.
Okay, well, thank you very much, Professor Ziegler. It has been a pleasure to hear you. It has been very illustrating both on the mistakes and on all the topics that you have touched upon. We are very glad to have you here in spite of all this terrible moment that we're living in. As you said, it's very true that it's a good opportunity to connect and have this event with all these people, and you coming here to talk to us. It has been a great pleasure hearing from you.
Thanks a lot for the invitation. All of you in Rio or wherever you are, stay safe. All the best. It was a great pleasure to meet you in this way.
Yeah, thank you.
Yes, thank you again, Professor Günter. We know that as the president of the Free University of Berlin, you are very busy, and we are very happy you could give us some of your precious time. Thanks also for Professor Bernardo Costa and Claudio Verdun for the discussion. Now we will go on a break for lunch. It will be 2 hours, and then we return with the lecture from Professor Tamara Broderick from MIT on a single switch interface for assistive technology. You can check our full schedule on our website, semap.rio.br. And see you soon.
See you soon. Bye-bye.
Bye-bye.